This experiment deals with dangerous chemicals, and proper protection must be used at all times. This experiment must be carried out in a fume hood or outside. The main use of P-Nitroaniline is as a precursor for a dye. However, a more interesting use for P-Nitroaniline is not as a dye, but in a reaction with sulfuric acid. Here is an example of the reaction I am talking about. Sulfuric acid is an extremely strong dehydrating agent, and with heat it is capable of tearing apart the P-Nitroaniline molecule to produce a long carbon snake. The carbon snake is made of mostly a carbon skeleton filled with a significant amount of CO2 gas and NO2 gas. This experiment actually requires a lot of chemicals, so I'm not going to read them all out. The 100 milliliters of concentrated ammonium hydroxide can be replaced with an equivalent amount of aqueous sodium hydroxide. Also, the ethanol is not absolutely required because it's used for recrystallization, but I highly recommend an ethanol recrystallization over one with water. In this reaction, there are two major steps. The first, nitration of the asetanilide, and the second is the acid hydrolysis of the acyl amino group. First, add about 34 grams of asetanilide to a 250 milliliter round bottom flask. I only had a single necked round bottom flask available, but a 3-necked round bottom flask would be ideal as it would allow for the use of an addition funnel. Next, 40 milliliters of anhydrous acetic acid was added. There was still a significant amount of asetanilide remaining in the container that I added it from, so I simply measured out 40 milliliters and added it to the container to wash out any remaining asetanilide. The solution of anhydrous acetic acid and asetanilide was then heated with stirring until all of the asetanilide had dissolved. I had to heat the solution up to about 65 degrees Celsius for everything to dissolve. It is very important to not let the reaction get too hot, as the asetanilide could get hydrolyzed to aniline. Wait for the reaction to cool to about 40 degrees Celsius and then add about 50 milliliters of ice-cold concentrated sulfuric acid. Be sure to add the sulfuric acid slowly. Once all the sulfuric acid has been added, place the round bottom flask into an ice bath. Also, at this point, you should put in place a thermometer. It should be noted that even after the addition of the sulfuric acid, the solution never got hotter than about 65 degrees Celsius. You should make an effort to never let the solution get hotter than 65 degrees Celsius. Leave the solution stirring on ice until the temperature reaches about 5 to 10 degrees Celsius. In the meantime, an ice-cold nitrating mixture should be prepared. With a beaker on ice, add about 20 milliliters of nitric acid. Let the nitric acid cool for a little bit. Then, add about 30 milliliters of concentrated sulfuric acid. Let the solution sit in the ice bath until it is ice cold. This should take probably about 15 minutes. Next, add the nitrating solution dropwise. The nitrating mixture must be added slowly, and the temperature of the solution must never rise above 20 degrees Celsius. We add the nitrating mixture slowly, and we keep the reaction at a low temperature because we want to prevent the asetanilide from being nitrated twice. Shown above is the nitration reaction that we are carrying out. On the left is asetanilide, and on the right are the three products that can be formed. The major product, and the one that we want, is 4-nitroacetanilide or para-nitroacetanilide. The 2-nitroacetanilide, or also known as ortho-nitroacetanilide, will also be formed, but it should be formed in much smaller proportions than compared to the para product. Finally, by keeping the reaction temperature low and by adding the nitration mixture slowly, we are able to keep the amount of the minor product 2,4-dinitroacetanilide at an extremely low concentration. A recrystallization will be done later to remove as much of the minor product as possible. You might be wondering why none of the products contain a nitro group on the 3 position of the ring. This is because the acyl amino group, which is the only substituent of acetanilide, is what is known as an ortho-para-director. Above you can see acetanilide and its various resonance structures. The far left is the common structure of acetanilide, and you can see that the electrons on the nitrogen are donated to the ring. You can see the 3 main positions that they land. Because these are free lone pair electrons, they carry a negative charge. These negative charges at these positions are attracted to the positive NO2 plus ion. You'll notice that these electrons never land on the 3 position or the meta position. Because there's no transient negative charge on that 3 or meta position, it is extremely unlikely for the positive NO2 ion to be attracted to those positions. Of course, though, a negligible amount of meta paranitroacetanilide is formed. However, such a small amount is formed, and for our purposes, we just ignore it. Once the addition of the nitration mixture is complete, let the solution sit for about 40 minutes. Do not let it sit for more than 40 minutes, as degradation of the product can occur or denitration can occur as well. After 40 minutes, pour the solution into 200 milliliters of ice water. The product is insoluble in water and should precipitate immediately upon addition. The yellow color of the precipitate is actually ortho-nitroacetanilide. The P-Nitroacetanilide is white or colorless, whereas the O-nitroacetanilide has a yellow color to it. Rinse the reaction flask with about 50 milliliters of cold water and add it to the beaker. Next, mix the precipitation mixture thoroughly, making sure that all of the sulfuric acid is dissolved in the water. Next, you need to filter off all of the liquid. You'll probably notice that it looks like the amount of product we have is significantly higher than the amount of acetanilide we started with. When wet with water, the product seems to significantly increase in volume. Wash your beaker several times with cold water to rinse out as much product as possible. There is still a significant amount of acid present in your product. However, don't worry about that, as the next step is a hydrolysis reaction, and we'll be adding acid anyway, so there's no use in washing away the existing acid and losing some of your product. I let my product dry under vacuum for quite a long time, but that's completely unnecessary, as in the next step we'll be adding it to water once again. What was interesting was as the product was drying, it took on a scrambled egg-like appearance. First, 100 milliliters of water was added to a round bottom flask. Next, 100 milliliters of hydrochloric acid was then added. After the addition of acid, add a couple boiling chips. The semi-dry, moist product was then chopped up using a spatula. The one benefit of drying this product to completion would be the much easier addition to the round bottom flask. I can tell you for certain that the addition of this moist product to the round bottom flask was extremely unpleasant and messy. This is what my product looked like when added to the round bottom flask. Next, a reflux apparatus was set up. I used the heating mantle, but you could alternatively use a Bunsen burner. Because the solvent we're using is water, there is really no risk of lighting it on fire. Once your solution has come to a boil and you can actually see water condensing back down into the solution, then you can start your timer. You want to boil the solution gently for about 15 to 20 minutes. The reaction in this step is known as hydrolysis. The acyl amino group in the P-nitroacetanilide is hydrolyzed to an NH2 group that you can see in the P-nitroaniline to the right. As your solution boils, the P-nitroacetanilide will slowly dissolve into solution. After about 15 to 20 minutes, add your solution to about 150 milliliters of water. Then let your solution sit and cool to room temperature. In the meantime, you should make a cold ammonium hydroxide solution. The ammonium hydroxide solution that you need to prepare consists of 400 milliliters of water, 100 milliliters of ammonium hydroxide, and 250 grams of ice. Once your reaction solution is cooled to room temperature, add it to the ammonium hydroxide solution. Your product should immediately precipitate. Then, filter off your solution. I don't show it here, but I was sure to wash the beaker several times to remove as much product as possible. Next, wash your product with about 100 milliliters of cold water. And this is what my final crude product looked like. At this point, if you choose to recrystallize, you can use water or ethanol. For demonstration purposes, I will recrystallize the product in both water and ethanol. If you choose to recrystallize with water, it will require about 30 milliliters per gram of product at a minimum. I would honestly avoid recrystallizing using water. Your main contaminant in your product is going to be ortho-nitroaniline. However, water recrystallization is not going to do a very good job separating these two isomers. However, if you do not have ethanol available, this recrystallization is better than nothing. However, if you do have ethanol available, this recrystallization is completely useless and a waste of time. The ethanol recrystallization will use about a tenth of the solvent, will boil much quicker, and will actually allow for a separation of the ortho isomer from the para isomer. This is what the crystals looked like after the solution had cooled to room temperature. The crystals were loosened up with a spatula, and then I vacuum filtered the solution. The solution was vacuum filtered, and the beaker containing the crystallized product was washed several times. The precipitate was washed twice with 100 milliliters of ice cold water. Afterwards, the product was left for a while to dry under vacuum. This is what the final product looked like, and you can see that it is significantly contaminated with the ortho isomer due to its evident orange color. Also, the melting point was about 25 degrees Celsius below the theoretical 145 degrees. I then took my significantly contaminated crystals and decided to do an ethanol recrystallization. I did my recrystallization in anhydrous ethanol, however 95% ethanol should suffice. The recrystallization with using the ethanol was much easier, faster, and will provide a better, cleaner product than the water recrystallization. A lot less ethanol is required for this recrystallization, but the most important point is that the ortho isomer is soluble in ethanol, whereas the para isomer is only sparingly soluble. This means that only the para isomer should recrystallize, whereas the ortho isomer should stay in solution. Once all the product had dissolved, the solution was removed from heat and allowed to cool to room temperature. As the solution cooled to room temperature, it was possible to see nice, clean, yellow P-Nitroaniline crystals crystallizing out of the solution. Once the solution had reached room temperature, it was placed on ice. This is what the final crystallized product looked like in the beaker. The precipitate was vacuum filtered and the beaker was washed with ice-cold ethanol. The product in the Buchner funnel was then washed also with a couple portions of ice-cold ethanol. This is what the final product looked like after letting it dry on vacuum for a little less than an hour. You can easily see that this product is much more yellow than the product obtained after the water recrystallization. However, these crystals still contain a significant amount of ethanol. I recommend that these crystals be crushed up using a mortar and pestle and then dried in a low temperature oven or left out in a well-ventilated area to dry. This is what the final dry P-Nitroaniline product looked like. The retested melting point was about 137 degrees Celsius, which was much better. And now to test to see if it works. About 5 grams of P-Nitroaniline was placed in a beaker, and then a few drops of sulfuric acid were dripped inside. The P-Nitroaniline was then heated until boiling using a Bunsen burner. At this point, I'll just take a minute or so to talk about the reaction in general. The final yield of P-Nitroaniline was an abysmal 15 grams out of a theoretical about 40. This gives a yield of about 38%, which is quite low. The main loss of product is probably due to the fact that there is a decent amount of ortho product that is produced in this reaction. And unfortunately, the production of the ortho product is not easily avoidable. The major avoidable loss of product was due to the fact that I did a double recrystallization, where in my opinion the water recrystallization was almost useless. My recommendation is to only do an ethanol recrystallization and forget about a water one altogether. Because we're simply dehydrating the P-Nitroaniline, the purity of the product isn't too important. If you need a pure product because you want to run another reaction with it, you're going to either need to do a second ethanol recrystallization or simply run a column. The final melting point of my product was still a bit low at about 137 degrees Celsius, which indicates that there is still a significant amount of impurities present. After attempting to complete the polymerization several times, I found that there are several factors that come into play that really affect the outcome of the reaction. I didn't have much P-Nitroaniline to play around with, but I did 2 main runs, one with a little bit of sulfuric acid and one with quite a bit more. This first one, I only used about 2 drops of sulfuric acid. A snake was produced, but it was not nearly as impressive as the ones that I'd seen on the internet. I'm letting this first reaction play out in real time so you can see what it looks like. The second one, I'm going to fast forward until it gets to the reaction. The remainder of this first reaction is about 20 to 30 seconds before it goes off, so you can skip ahead if you are impatient. I did not have enough P-Nitroaniline to test this thoroughly, but I believe that the ratio of sulfuric acid to P-Nitroaniline, as well as the container that the reaction is carried out in, plays a big role in the final result. I believe that the walls of the beaker were too high compared to the level of the P-Nitroaniline, and I believe this negatively affected the results. This reaction was done with about 10 grams of P-Nitroaniline with at least 10 drops of concentrated sulfuric acid. The reaction was clearly more violent, and I believe that the correct amount of sulfuric acid to use is somewhere in between the amount that I used in both runs. Of course, taking into account that double the amount of P-Nitroaniline was used here. Although I did not achieve the result that I was expecting, I'm still satisfied with the results. Subscribe if you would like more. I try to upload at least one new video a week. Also, feel free to make suggestions as to what you would like to see next.